Hey everyone, welcome. I'm so excited to be able to share this lesson with you. Today we're going to learn about the derivative, one of the most absolute remarkable achievements in human history. The derivative is surprisingly approachable, I think. I feel that that what's so neat about this is that you're about to learn not something new, but simply an application of what we've already been learning. So, with that in mind, I think you can just kind of figure it out without me telling you too much. Well, that might be a bit of an exaggeration, but it really is right there at your doorstep. So I want you to do your best to answer these practice questions, and we'll go over them. It's okay if you don't get them right, because I just want you thinking about it to kind of see the reasoning that went on to develop this important concept that we call the derivative. So, if you would please pause the video, read through the problems carefully, and try and answer all of practice 4.1 A through C. And then we'll talk about it and see if we can glean something from it. Okay, I hope you enjoyed that. Let's take a look. Consider the graph below of f of x equals 1 half x squared minus 1 and the point on the curve at 2, 1. Suppose we wanted to find the slopes of the secant line from 2, 1 to other points on the curve. Find the slope of the secant line through 2, 1 and x equals 6. Carefully draw the secant line. Okay, well, I'm going to try that. Let's see. At x equals 6, I'm up here at 17. So I have a line tool, so hopefully I'll be able to do this with somewhat ease. Okay, I think I got that okay. And I can maybe even stretch this out a little bit. There we go. Well, I lost it. There we go. Okay, so I've got my secant line. All right, we're going to find that slope. The slope is this y coordinate, 17, minus this y coordinate, which is 1, over this x coordinate, which is 6, minus this x coordinate, which is 2. So I get 16 over 4, which is 4. That is the slope of the secant line. It's up 1, 2, 3, 4. 1, 2, 3, 4 over 1. 1, 2, 3, 4 over 1. Cool. All right. Let's find the slope of the secant line now from 2 to 1 at 2x equals 4. Excuse me. Always 2 to 1, but this time to x equals 4. So I still got that little dot there. I want to go, because that goes right there. So it's not quite as steep this time, is it? It's going to be difficult probably for me to do this, but I'm going to try. Oh, I shouldn't use red. Hold on. Let's use green. There we go. I think that's pretty close to right. I can kind of adjust it. There we go. Okay. So we've got a secant line. Now let's find the slope of this one. So the slope here is the y coordinate is 7 minus this y coordinate is 1 over the x coordinate is 4 minus the x coordinate of 2. So that is 6 over 2, which is 3. Just as we said, it's not quite as steep. Up 1, 2, 3 over 1, up 1, 2, 3 over 1. All right, let's find the slope of the secant line from 2, 1 to x equals 0. So this time we're going to go to x equals 0, apparently. Well, that would be like here, right? Through here. So that's quite a bit less steep, right? All right, and that would be the y coordinate at 0, which is negative 1, minus the y coordinate at 2, which is 1, over the x coordinate of 0 minus the x coordinate of 2. So it's a negative 2 over negative 2. That's just equal to positive 1. All right, so now I want to keep that up there, so I'm just going to scroll down a little bit here. What is the general formula for finding the slope of the secant line to f from the point 2 comma 1 to x comma f of x. So I want you to try and do this. I know it's an example, but like I said, I really want you to try and work through this yourself. So write a general formula for the slope of a secant line from any point from 2 comma 1 to any point, any x value, but it's going to be a curve. It's going to be a point on this curve, so it'll be an x value and then f of that value. That's why I have x comma f of x. All right, so the slope should be the y value f of x minus, what's the y value? We're always going through 2, 1, right? So it's always been minus 1. If you look back up here, every one of these times it was minus 1, minus 1, minus 1. The only thing that was changing was that y value and the first x value over x minus 1. Okay, now draw a tangent line to f at point 2, 1. Why can you not use your formula from part D? Oh, I'm sorry. I should say part A. Well, let's see here. Let's draw a tangent line. I'll use brown, I guess. Kind of run out of the pretty colors, I guess. So a tangent line, we're just going to come down here. We're just going to graze the edge right there. So there's my tangent line, right? So it's got a slope that's bigger than this blue line of 1, but it's less than the 3 and the 4 from before. So draw an approximate tangent line. Why can you not use your formula from part A? Why can't we use this formula? Well, do I have another point that I'm going through? What would my other x value be? Well, you could say that I'm using this point right here. I'm only using the point 2. In other words, I'm finding the secant line from 2 comma 1 to 2 comma 1. I'd be dividing by 0, wouldn't I? I can't do that. All right, I've got another practice problem for you to do. All right, so if you would do practice 4.2, A, B, C, D, and E. So pause the video, give it a shot, and then we'll talk about it. Okay, let's see what you came up with here. Draw an approximate tangent line at x equals 3. Okay, I can do that. So an approximate tangent line, probably something kind of like this. Well, that might not be quite right. Maybe a little bit steeper, and then maybe move it over a little bit. All right, something like that, right? Something like that. Okay, next we need to, what is the general formula for the slope of a secant line to f from x equals 3 to some other x? Well, we did that on a previous example, didn't we? We know that the slope of the secant line is going to be f of some other x value x minus f of 3. Well, what is f of 3? Well, f of 3 is 0, right? All over that other x value minus my x value 3. We're going to use a calculator to complete the table of values for the slope of the secant line to f from x equals 3 to the given other values of x if possible. So let's pull up Desmos. And we could use any calculator that we really wanted to, though. But I'll just use this one. And we said f of x, right, was, let me pull that up, negative 1/3, right? X cubed plus x squared. And we are going to find the slope to be f of, I'm going to say f of 4, we'll do that one, minus, it was 0, right? So I guess I don't really need that. Over x minus 4. No. X minus 4 minus 3. Like that. So this first one here should be a negative 5.3333333. Okay, let's try the next one. Next we have to do, I don't know, it bothers me not having that second term there. It doesn't look like y2 minus y1 over x2 minus x1. That's what all right, 3.5 over 3.5. So we have negative 4.083. All right, let's get the tangent line to 3.2. So we're just inching closer and closer and closer to x value 3. I get negative 3.4133333. So this one is negative, wait, I forgot it already. 3.413. All right, let's try 3.1. Negative 3.203. All right, I got 3.01. And I can keep doing this, can't I? As long as I'm not dividing by 0, I can just keep getting closer and closer and closer. I get negative 3.020. So that looks like it's getting closer and closer and closer to negative 3. And what we're doing is we're drawing different secant lines to different places. So we did it to 4, which was like this. And then we did it to 3.5. And each time it got a little bit less steep, right? And then we did to 3.2. And what I want you to see is as we move closer and closer and closer to that point, and it's difficult to see here, they're kind of overlapping too much. We're getting closer and closer and closer to that tangent line. I'm just going to take those off real quick, though. All right, let's try 3. Now, there's a problem there, though, right? I can do the numerator, but it's going to be, the top's going to be 0. And then when I put 3 minus 3 on the bottom, it's undefined. So this is not going to work. This is undefined. I cannot... Oh, I'm still in line mode. I cannot use my slope of the secant line formula to find the slope from x equals 3 to x equals 3 because this is the same point and I end up dividing by 0. All right, let's try 2.99. All right, this is a negative 2.98. Oh, 980 actually. Then 2.9 was negative 2.803. And let me fix that one. That was negative 9.80, not negative 9.88. There we go. Easy to fix that. All right, and we have at 2.8, we're probably going to be getting even less steep, I'm guessing. Negative 2.613. And what about it 2? Negative 1 and a third. All right, so as we look at this, so one way to describe a tangent line at x equals 3 is as a secant line from x equals 3 to x equals 3. Well, what technique that you have learned last unit could help us find this tangent line slope? So could we estimate it? Could you look at this? Do you look at this table of values? Do you have any guess what you think the slope would be of the tangent line if we could actually figure it out? Well, hopefully you agree with me that it's looking like it's going towards negative 3. And I could probably use the calculator and spare myself having to write it in there and just keep going closer and closer to 3. And I can just keep adding a 0 here as I get closer and closer and closer. I mean, it's getting pretty close to 3, isn't it? As I add those zeros, it's getting closer and closer and closer. Well, what technique could we use? I hope you realize that this is a limit. We just need to take a limit. This is something we already know how to do. It shouldn't faze us that we can't actually do this because we can use a limit to get around it. So we're going to write an expression that can be used to find the slope of the tangent line at x equals 3. So let's find the slope of the secant. Slope of secant line. Now, secant line is the line that goes through the graph at 2 places, right? So the slope of a secant from x equals 3 to some other x. All right, so that would be that slope would be f of that other x. We have to get the y coordinate minus my y coordinate 3, so that'd be like f of 3, right? Over x minus 3. In this case, f of 3 was 0, right? So a limit expression, we just need to get this x value really close to 3, right? So I'll just say the limit as x approaches 3 of f of x minus f of 3. All over x minus 3. This is equal to what we call the derivative at 3. F prime of 3 is how we write that. That's called f prime. That means the derivative of f at x equals 3. So the derivative, and for a while I'm going to try and stick with one symbol, but it has several. The derivative is written f prime. If it's y equals, we can say y prime. It's also written dy dx. That's change in y over change in x. Lots of different ways, but we're going to stick with this way for a while. And it means the slope of the tangent line at x equals 3. That's what it means. Well, you know, I didn't actually ask you to find it, though, did I? But, well, maybe we'll come back and do that. I'll leave you to do that in yourself. We'll look at an example of how to do that, but I want to go through and get this discussion finished here. But we could take that limit, couldn't we? Probably wouldn't be too hard. All right, let's take a look here at our notes. All right, so the slope of a tangent line to f at x equals c is the derivative of f at c. It is denoted f prime at c, as well as those other notations I said, but let's stick with just f prime at c right now. The alternative definition of the derivative at a point x equals c. The derivative of f of x at x equals c is f prime of c equals the limit as x approaches c of f of x minus f of c over x minus c. That is the formula that we just came up with. Hopefully you came up with it with me. That if I've got a point that I'm trying to find the derivative at, call it c, that I just need to find the equation for the secant line to some other point x, and I subtract their y coordinates. That'll be f of x minus, our c was 3, so it was f of x minus f of 3, but you know I'm just using c for some number, over x minus that c. And then we just simply take that x value and take the limit as it gets really close to it. And of course we have to check, you know, both sides. That is actually what is called the alternative definition. I don't know why one gets the title of alternative and the other one gets the title of the definition. To me, they're both equally good. But the other definition is just called the definition. So the other common definition is written in terms of the value h. The h is the size of a horizontal move from one x equals c to some other x that is h units away. And that is f prime of c is equal to the limit as h goes to 0 of f of c plus h minus f of c all over h. So let me draw that out. Okay, so if I have a value that I'm trying to find the slope of the tangent line on, let's say this one right here. So this is my c, okay? Then what we're going to do is we're going to take a secant line and we're going to describe that secant line as being some units away from c of h, okay? And so if this was c and I move h units to the right, or then this is c plus h. And then this here becomes the point f of c plus h. This point down here was just f of c. And so to get the slope of this secant line, I need f of c plus h minus f of c. Those are the two y coordinates, that y coordinate and that y coordinate, all over. Now I got to subtract our x coordinates. C plus h is that x coordinate, and the other x coordinate is c. Well, you could see that the c's cancel out, right? So that's why there's just an h in the bottom. And so the advantage of that formula is you have a denominator that is a single quantity. But, you know, I think sometimes it's easier to find the derivative with the alternative. Other times with the regular definition. It just depends on the problem or how bored you are. Lastly, though, we need to look at the general definition. So both of these definitions can be used to find not just the value of the derivative at one x value, say 3, but we can find it in general. We can find a function that tells us the derivative at any x value. And but typically I will use the definition of the derivative to find it just at an x value, but I can use either one. So here it is. The derivative of f of x is denoted f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. When these limits exist at x equals c, we will say that the function is differentiable at x equals c. If the limit does not exist, or if the the limit is undefined, we'll say that it is not differentiable. Okay, let's do an example. Example, f of x equals x squared minus 4x. We're going to sketch the graph of f and the tangent line to f at 3. Knowing what the graph looks like is a great advantage in AP Calculus because it gives you the way to check your work, a way to predict what your answer should be. So we're going to sketch it mainly for just that reason. So this can be factored to x times x minus 4. So I hope you see that this graph has a 0 on the origin and at x equals 4. And I'm not going to worry too much about the y coordinates of the graph. I just want to get the general shape of how it looks like, because hopefully you realize it's a parabola. Well, that's possibly the worst parabola I've ever done. Okay, I still didn't do it very good, but oh well, I'll give up. All right, I want the tangent line at x equals 3. So the tangent line at x equals 3, it's going to have to be something like that, right? It's probably quite a bit deeper than that, now that I think of it, because I bet this goes down a lot more. But it's going to have to be going up, right? We think it's going to be a tangent line slope that is positive. So let's find the tangent line slope and see if it is indeed a positive number. Remember, the derivative tells you the slope of this tangent line. So this tangent line right here, its slope is equal to f prime at 3. That's what it tells you. That's the purpose. So let's use the derivative to do that. X squared minus 4x. Okay, so we're using the definition of the derivative, not the alternative one that we derived first. So we're going to do the limit as h approaches 0 of f of x plus h minus f of x all over h. I can't see it because I scrolled down, but f of x is x squared minus 4x, right? Okay, so let's keep that in mind. All right, so f prime of 3 is the limit as h approaches 0 of f of 3 plus h minus f of 3 all over h. So I just simply replace the x's with the 3. Now f of 3 is 3, f of 3 plus h, would be 3 plus h squared minus 4 times 3 plus h. And then f of 3, we can just figure out f of 3. I'm going to just do that over here on the side. That's 9 minus what? 12? That's negative 3. All right, I just want to take a second to make sure that you're okay with that. I do need to write limit here, but I want to make sure that this is clear. A lot of students get confused with this step. When I say f of 3 plus h, that means that I have to put 3 plus h in everywhere there's an x in f of x. So I got to make 3 plus h squared and minus 4 times 3 plus h. And that's before I even leave this first f of something, before I get to this f of 3. A lot of people forget the second part. They won't put it in both places or something like that. All right, and we need to write the limit each time until we plug in, right? Okay, so let's just do some algebra. We could go ahead and plug in 0 right now, but I think you can see it will give us 0 over 0. It would give me 9 minus 12 plus 3 is 0. So we're going to do some algebra. The limit as h approaches 0 of 9, square that, multiply the two together and double it. When you square a binomial, you'll square the first number, multiply these two terms together and double them, and then square the last number. H squared, distribute the 4, minus 12, minus 4h, and then minus a negative is plus a positive. Now, if we've done this correctly, everything that doesn't have an h in it should go away. So let's make sure that. We have 9 plus 3 is 12. All those things there go away. Agreed? So what we have is a 6h minus a 4h is 2h plus h squared all over h. Now that I have that, I can either factor an h out or simply, because it's a monomial, I can divide it into both terms, making this the limit as h goes to 0 of 2 plus h. Now I'll plug in 0 for h, and I get simply 2. So we know that the limit as h approaches 0 of this function was 2. So that must be f prime of 3. That is the slope of this line. All right, let's check our work using the alternative definition of the derivative. So same problem. We better get the same answer. We're just going to use the other form. So the other form says that f prime of c is equal to the limit, and that's not an h, it's x approaches c, of f of x minus f of c all over x minus c. So f prime of 3 would be the limit. See, I'm replacing c with 3, so all my c's becomes 3's this time, not x's. X approaches 3 of f of x minus f of 3. What was f of 3, by the way? We did earlier. I want to say it was like 9 or something. Or negative 3 or something. 9 minus 12 is a negative 3, yes. All over x minus 3. All right, what is f of x? Well, we know that. That's just a formula that we were given. X squared minus 4x. Minus a negative 3 is plus a positive. Now, if I try and plug in 3 right now, I would get 9 minus 12 is a negative 3 plus 3 is 0 over 0. So this is indeterminate, but I can factor it. And what's cool is you're always going to be able to. It's like calculus magic that this will work every time. Well, unless it's not differentiable, I guess. But if it's differentiable, this will work. So I need x minus 1? Okay. All right, those reduce out. I'll just write this over here. So I have the limit as x approaches 3 of x minus 1. I plug in 3, I get 2. So we know that f prime of 3 is 2. We better because we knew that ahead of time. One more thing we're going to do, we're going to get the actual function of fx, and we could actually look at the derivative at any value, but we'll then check it by plugging in 3. So we're going to do this one more way. We're going to get the derivative equation and evaluate it. So we looked at using the definition of derivative to find the derivative at a specific x value. We looked at using the alternative definition to do that. Now we're going to use the definition to find the equation. So f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So since I'm finding an equation, don't be surprised to have x left over our answer. In fact, we expect to most times. Our f of x was, let's see here, f of x was x squared minus 4x. So I have the limit as h approaches 0, f of x plus h, which means I got to put x plus h everywhere there's an x. So it becomes x plus h squared minus 4 times x plus h. That just took care of this part here. Now I have to do the next part, minus f of x. Well, what is f of x? It's x squared minus 4x. Okay, now, if we do this right, everything that doesn't have an h in it should cancel out. All right, I'm going to square x plus h. I get x squared plus 2xh plus h squared. You can FOIL that if you want to do it by hand, but it's always the first thing squared, times 2 together and double it, and then square the last one. Minus 4x minus 4h. And then I have a minus x squared plus 4x all over h. Okay, let's see what happens. X squared with the minus x squared. Negative 4x with the positive 4x. Everything else has an h in it, so we're good. The limit is h goes to 0 of 2xh plus h squared minus 4h. And the reason why I'm happy that everything has an h in it is that if I have a rational expression, and as long as every single term has an h in it, then I can divide each one of these terms by h, giving me the limit as h goes to 0 of 2xh over h is 2x. H squared over h is just h. Minus 4h over h is just a minus 4. Now I plug in 0 for h, and it gives me 2x minus 4. That is the derivative as a function of x. And if I plug in 3, I'll get f prime of 3 is equal to 6 minus 4, which is 2, which is exactly what we said. So that is pretty exciting stuff, right? All right, that's it for today. Tomorrow we're going to look at this again, but maybe from the eyes of Newton. This was more looking at it geometrically, which was the eyes of a guy named Leibniz, Gottfried Leibniz from Germany. Tomorrow we're going to look at a little bit of physics. I hope you're excited about that. I will see you then. Take care.